One final example of being able to find a volume over a general region of a 3D function. We have the volume that lies under the paraboloid z equals 3x squared plus y squared. Excuse me. The region is bound by the functions f at y equals y, g at y equals y squared minus y. I went ahead and I graphed the functions. This is the function g. This is still g. And then our function f is just going to be the linear function. All right. And what I'm going to do is I'm not too concerned with anything except for the region that's enclosed. So this area right here is the one that I really care about. So I'm just going to transpose that and just draw it at the bottom here. If I do so, we get this sort of shape in quadrant 1. So we get this linear thing going, and then we have this going. Okay. And again, our functions, this is going to be g, which is the linear function, and this is going to be f, which is our quadratic function. All right. Now, when you're thinking about this, you need to know whether it's going to be a type 1 or a type 2 region. Now, as a type 1 region, remember type 1's up and down, this is what would happen. We could express this as a type 1 region. And I want you to notice as a type 1 region, especially on the left-hand side, that any time that you're to the left of the y-axis, the quadratic's only touching itself. Anything to the right of the y-axis, the quadratic and the linear function are touching one another. That means that you would need one double integral to represent the left side, and then you would need another double integral to represent the right side if you were to do this as a type 1 region. However, as a type 2 region, where we draw from left to right, I want you to notice that the function f touches the function g each time exactly once. And we don't have that problem where one function only touches itself and then one function touches the other function. So clearly it's better to express this one as a type 2 region. That way we can avoid the two different integral technique. Certainly if you want to, you can use the two integral technique, but let's just use a type 2 region. All right. So from left to right, the quadratic's the lower bound, the linear is the upper bound. So we're going to say that going from left to right is x. X is going to be y squared minus y to y. And then of course, you could probably inspect that 2 is going to be the limit of integration of the intersection of the upper bound. 0 is going to be the lower bound. However, let's just work it out just to verify. We're going to set y squared minus y equal to y, which means that y squared minus 2y equals 0 by subtracting y from both sides. That means that y minus 2 is 0, so that means that y is 0, y is 2. All right, so in this problem, the range for y is going to range from 0 to 2. And that's our domain D. This is the important part that we need to hold on to because this enables us to set up the double integral at this point. So we're going to set up the double integral. Double integral 0 to 2. Lower bound y squared minus y. Upper bound is y. Integrand 3x squared plus y squared. Notice that we went from left to right, so that means that we have to take care of dx first, and then we solve for y, so that means we take care of dy next. Right. Integration's not too terrible, but not too fun on this one. We're going to add 1, divide by 2, or divide by the new exponent for each of these. So we're going to end up with respect to x, that's going to be 3/3 x cubed. Since there is no x term, it's a constant, xy squared. That's going to go from y squared minus y to y dy. At this point, you probably see that this is not going to be a lot of fun because when we substitute, y is pretty easy. All right, so by substitution, 3 over 3 is 1, so we get y cubed plus y times y squared. So that's not too bad. Here's where it gets a little bit ugly. We're going to get y squared minus y cubed plus y squared minus y times y squared. And then we still have the dy out there. Good news is it's polynomials. Bad news is we got a lot of foiling to do. All right, it's especially right here with this animal. So I'll come back to that in a moment. Okay, but for right now, let's just do all the other stuff. So by integration, we have 0 to 2. And then we're going to have y cubed and y, I think this should be a y square. So I think I might have made a type or a righto here. All right. So we're going to get y cubed plus y cubed. That should be 2y cubed. That should be pretty easy. Okay. Minus, so here comes the hard part. So minus, now when we FOIL this y squared minus y cubed out, okay, it's going to be a little bit ugly, but it shouldn't be too bad for us. I'm going to do that in red. All right. So when we cube out this part right here, we're going to get, I think, 4 terms for this. I think we're going to get y to the 6th minus 3y to the 5th plus 3y to the 4th minus y cubed. Check that, but that should be what we end up with. Right. We still also have to distribute the negative to this y squared minus y times y squared. All right, so it's still going to be a little bit ugly. So we also have minus quantity y to the 4th minus y cubed. So we'll have the dy there. All right. We could do a little bit more simplification with this. All right, and it's not going to turn out too badly. 0 to 2. So we have, if we look at this, we have 2y cubed. We have minus a minus y cubed, so that's 3y cubed minus a minus y cubed, so that's going to be 4y cubed, which is nice. We have this minus y to the 6th, nothing we can do with that. We have this minus 3y to the 5th, minus a minus becomes a plus 3y to the 5th, so nothing we can do with that. And then finally, I notice that we have a negative y to the 4th. We also have a negative 3y to the 4th, so that should be negative 4y to the 4th dy. So check that out just to make sure everything's okay with going through with that, but that should be our algebra. That's the hardest part of the problem. The rest of it's fairly simplistic. Right? We're going to evaluate term by term with integration. So now we're going to get 4 over 4 y to the 4th minus 1/7 y to the 7th plus 3/6, I'll just leave it as 3/6 for now, y to the 6th minus 4/5 y to the 5th from 0 to 2. We're going to substitute. 0 doesn't matter, as it hasn't in the previous problems because we have polynomials. So now we're going to get 2 to the 4th minus 2 to the 7th over 7 plus 2 to the 6th over 2. So notice that 3 over 6 becomes a half. Okay. Minus 4 times 2 to the 5th over 5. All right. If you'll give me a moment, oh, minus 0 because of the lower bound. Now I'm going to shove that into my calculator, and I would recommend that you do the same just to make sure that I'm doing this correctly. So I got 144 over 35. So check that solution, make sure it makes sense. And again, that's an illustration of how to utilize the type 2 integral to be able to evaluate the volume.